Good evening and a big welcome to this webinar on BIM for Geosciences hosted by NGI and Geovita. My name is Magnus Rømon and I'm head of the environmental geotechnics sections here at NGI. The background for this shared webinar between Geovita and NGI is that we together have worked with developing new routines for 3D and BIM modeling the last year, which we now want to share with all of you. Before that, we have worked together on several large projects for many years, so we really know each other well. Before we start with the fun part, I will shortly introduce the two companies. Geovita is a consultancy which started up in 1991, and they have their offices here in Oslo. They are approximately 15 employees and work with geotechnical engineering and rock mechanics on large construction and transportation projects. NGI is a private research foundation with head offices in Oslo and offices in Trondheim, Perth, and Houston. We are approximately 320 employees from 40 different nations and work with both consultancy and research within the four market areas of geodata and technology, geotechnics and environment, natural hazards, and offshore energy. Both Geovita and NGI are currently working with some of the biggest engineering, construction, and infrastructure projects in Norway, run by both private and public companies. So, short about today's agenda. The first part is soon finished. After that, Mats will have a short introduction to the context and the tools that we are using. Second, Per Anders will present about modeling of soil layering for large projects, before Nikolai finishes with a presentation about both parametric modeling of dynamic sheet pile walls and also some on communicating uncertainties in the models. Normally, we would have loved to have an open up for a discussion at the end, but since we are running this through a platform we are using, which does not enable that facilitation of a discussion, and since we have more than 900 persons who signed up for this webinar, we will solve this question part with a chat to the right. So if you have any questions, please post them in the chat, where you can also like the question that all other people have posted. And then we will post the answer on these questions on the landing page, which you all used for signing up for the webinar. The recording of today's webinar will be posted on NGI's YouTube channel, so please feel free to watch the video out there afterwards, or you can also share it with some of your colleagues later. In the presentations, we will be using quite a lot of videos. In the test run we had a few days ago, these videos did not run as smooth as we wanted. This is something that we have tried to fix, but we are not sure if we managed. So, but these videos should run smooth in the film that we post on YouTube afterwards. So if you are having problems viewing them today, that might be an option seeing them later. So that was the practical information. Now over to Mats and the first presentation.
Okay. Hello. So my name is Mats Karlström. I work as a geotechnical engineer at NGI, and I'll kick off this webinar with giving you an introduction to the topics of today and setting the scene for the following parts. I'm not sure, can you see my screen now, or is it another view showing? Great. So if you focus on infrastructure projects and geotechnical engineering, the subsurface in urban areas is becoming more congested, increasing complexity for new developments. Projects also become bigger and more agile as design and construction phases are done in parallel. With digitalization, cloud storage, and smarter sensors, we're able to collect more data. And from this data, we need to harvest more insight to increase our knowledge base, such as with machine learning. Finally, we geotechnical engineers must be prepared for the drawing-free projects that are coming and adapt to a more model-based design workflow. In light of this, Geovita and NGI has seen the need to revitalize the way we work so that we design smarter and manage data in a more structured way. We also need to encourage improved standardization across our disciplines. So in this webinar, we'll show a few insights on how we are currently trying to work smarter than before and how to improve our communication, especially by using visualization. So let's say hello to our geotechnical engineer. In his day-to-day work, this engineer is surrounded by an ecosystem of applications and tools, enabling him or her to get the job done. This ecosystem of applications is very much alive, and probably within a year or two will look much different again. But for now, this looks like a pretty organized picture. However, in reality, when accounting for how data is transferred between each application, it might look something like this. And our design workflow often involves transferring input and output from one application to another. And that's simply the way it often has to be. So it's therefore important that we push for using open and non-proprietary data exchange formats, such as IFC, JSON, GML, or other formats depending on our need and purpose. But let's clean up the picture a bit here and start over. So I would like to introduce part 2 of this webinar, and this will focus on developing a ground model using the software Leapfrog Works. We also use a few other applications in this work, both for data pre-processing with Excel and Python, but also for visualizing model results like in a GIS environment. A big part of the job for a geotechnical engineer is to create an understanding the ground below, characterizing material properties of rock, sand, silt, and clay, as well as predicting its behavior at small and large scale. Ground investigations are a key component in acquiring information from the ground, and all data that is collected is analyzed and interpreted, forming the basis for a ground model to be created. Data quantity for some projects can become quite large, as shown here in the figure to the right. And in this figure, we can see all the sub-areas, boreholes, and lithological interpretations for a single ground model in one of our projects. So it's therefore important to be disciplined in the way we collect, manage, store, and visualize ground information and results. And you also need to use a software application that is capable of dynamically updating the model as you go along during the project, acquiring more and more data from soil investigations. In summary, soil investigation data obtained using, for example, a drilling rig or other method is turned into a graphical visualization, and that is the ground model. And more on that in part 2. So if we clean the canvas again and say hello to our geotechnical engineer, for part 3, we will dive into parametric modeling using Rhinoceros and Grasshopper. You could also opt for using, for example, Revit or Civil 3D in combination with Dynamo, but for us, Rhino and Grasshopper is so far our preferred choice. So to set an example and introduce the concept of parametric modeling for those of you who are not familiar, if you imagine these ground improvement columns sketched in blue on the photo, their geometrical properties and attributes may be represented in a sketch as something like this. And from these properties, or by using these properties with the concept of parametric modeling, we can apply some logic and algorithms to digitally generate the geometry and information in 3D space. So to explain this a bit easier, I'll show a quick example where I'll create a conceptual script that generates the row of columns that you saw on the photo on the last slide. And this view here shows a split screen between Rhinoceros to the left, which is more or less a traditional CAD interface, and the Grasshopper visual programming canvas to the right. So in Rhino, if I start by creating a single point in space, I can connect this point to the Grasshopper canvas using a point object. And then I can use a move object along the x-axis vector to move this point with the distance that I can control with this slider here. And as you can see on the screen, I have now created 2 points. I then connect those 2 points using a line object and further divide that line into multiple components. The number of components I can control with the slider like this. So now I have created the base center points of my columns. And in order to create the top center points of my columns, I use a move object and a vertical set vector and another slider component. And in this way, I can move all my base points vertically upwards using a distance of my choice. Now that I have both the top and the bottom center points of my columns, I can use another line component to create the center lines of the columns. And as you can see here, I can vary the geometrical properties. Finally, I can use a pipe component and another slider controlling the radius to create pipe objects in 3D space along my center lines like this. And in this way, I have quite quickly created a script that can generate 3D columns where I can manually change the geometry of my choice using the sliders below. But more on this in part 3, where Nikolai will show a similar workflow for sheet pile retaining walls, and also how to visualize uncertainty on a bedrock surface. But first, Per Anders is going to show how he can create a ground model like this.
Hope you can see my screen. My name is Per Anders Mortensen and I work for NGI. I'm going to present to you about the modeling of soil layering. I'll just jump right in. We look at the specific project where I have made a 3D model of the soil layering. This is a railway project in Norway, intercity Drammen to Kobbervikdalen, where the contractor is Bane Nor and the entrepreneur is Veidekke. The part I have been involved with is 540 meters of cut and cover and then 270 meters of soil tunnel. The software we use to model the soil layering is called Leapfrog Works. The first thing you do in this software is import boreholes, which is quite easy. You import an Excel sheet with the coordinates, and this can be exported from most geotechnical databases and imported directly. Then I have another spreadsheet where I have the same borehole name and my interpretation. So I put from that from 0 to 2 meters, it's topsoil, and then from 2 to 10 meters, it's clay, and so on. This is then your interpretation of the soundings conducted. So in this model, the pink color represents topsoil, the blue color is clay, and then the green is moraine. In this project, we have a mix of different methods. In total, we have 101 boreholes. And at 12 of these locations, we have performed rotary pressure soundings, while we have performed total soundings in 87 boreholes. And at 10 locations, we have CPTU data, and at 11 locations, we have performed piston sampling. For those who don't know total sounding, it is a method that combines rotary pressure sounding with bedrock drilling. But all of these methods have very different levels of uncertainty attached to them. Piston sample is quite certain, while your interpretation of a total sounding is much more uncertain. The 3D visualization is then very good to have so that you can, in some sense, calibrate your interpretation of the soundings based on the samples you have nearby. The next thing to do is import the terrain surface. And then I create the bedrock surface, and you can also create a groundwater surface. You just import the coordinates from where you have data on the groundwater level or bedrock, and then you interpolate between the points. There are different ways to interpolate. If you think the bedrock surface or groundwater surface follows the terrain, you can interpolate based on the depth instead of on the elevation, which is what I've done in this project. When you have created the bedrock and terrain surface, you put them as boundaries, and with a few clicks, make the software interpolate between the boreholes. I have also added a distance boundary to the boreholes of 100 meters. The strength of this method and software is the visualization. It is easy to spot errors in the dataset or with your interpretation. And you can play around with how you interpolate or set up your model until you're happy with the result. Another great thing is how easy it is to add another borehole or more boreholes. You just put the coordinates into the spreadsheets, upload them, and then the whole model updates within a few minutes. The next thing you can do is import structures and ground improvement. And there are two good reasons for doing this. It is a great way to spot the potential problems, especially in the early stages of a project. Then you might not have great models, but you can just import the alignment of the railway or something else that helps you visualize the construction area. And the other reason is that you can add your structures to your cross sections and profiles. So here you can see the cut and cover section to the left. And the diaphragm wall is the orange wall. And you see that in the bottom of the pit, we have a jet grout arch due to uplift. And to the right in the screen, you see the soil tunnel and some of the ground improvement there. And then the soil tunnel goes into a bedrock tunnel after a while. Yeah. The models you saw of the sheet pile and the diaphragm wall and the jet grouting arch have all been created using parametric modeling, which Nikolai is going to talk about after this presentation. So then I'll talk a bit about drawing and exporting from the model. First off, you can create a profile along the railway alignment or any other line, which is what you see in the right corner. Here I have added the boreholes and the culvert. And then you can also create cross sections along the alignment every 5 meters, for example. And these are created automatically. You can export them to a PDF and then look through them and decide which one you want to do calculations on. You then export the cross sections to a DXF format, which most calculation software support. In this project, this has greatly increased the efficiency. We created a Plaxis 2D model with interfaces and materials and so on. And then you just copied the calculation, removed the layering, and imported new layering from another cross-section. Since the cross-sections are based on the railway alignment, they are all centered correctly, so you don't have to move anything or decide the position of the center of the building pit. You can have the new calculation up and running in a very short time frame. Lastly, you can export depth to bedrock, soil thickness, or the thickness of the clay layer. This can be imported to, for example, ArcGIS, where we have a template. You add some contours, and then you can export and deliver. All the cross sections in the model update automatically if you add boreholes or change the soil layering. And then you, of course, have to export to Plaxis and do the calculation, but it still streamlines the workflow very much. So if you get a new sounding, I add some data in a spreadsheet, and then in 10 minutes, I can have a new updated map of the bedrock surface. Lastly, we have done some coloring. so that you can visualize uncertainty based on the distance to the boreholes. And this model is what I export for the customer. You add some attributes and export as IFC, so that the customer can view the same thing as us in his BIM collaboration tool. Giving the contractor this model, together with easily creating cross sections and profiles, have really simplified the communication on geotechnical issues. It is much easier to explain to someone with little background in geotechnics when you have some illustrations. And here with this model, it takes very little time to create these illustrations. And also this quite simple visualization of uncertainty have been very good regarding where we should have some supplementary soundings, and also explaining to the contractors why we need this. Yeah, and Nikolai will also talk some more about visualizing uncertainty in the Bedrock model. So to sum things up, I think 3D modeling of the soil layering is not just something we should do in order to meet some delivery. It is actually a great tool for us to streamline our work process, simplify communication to the stakeholders, but it also gives us a very good understanding and visualization of how the soil layering is in the area, which simplifies the interpretation process. Today I've talked mostly about a large infrastructure project, but on smaller projects, this is also time effective in my experience. It is also more precise, comparing it to projecting the soundings onto a cross-section and then manually drawing the layering. And when you later on need some illustrations for the report, then you don't need to draw them from scratch. I would also say you get the most out of the model by setting it up early in the project. And then you can enjoy having good illustrations for meetings. And it is also very nice to get the layering done in some sense. Because then you have a best guess of the layering based on the currently available information. And you don't need to go back and forth for each new cross-section you decide to do calculations on. At the same time, you need to be aware of the uncertainties, but I think the model also helps with illustrating and visualizing that to some extent. Yeah, I think that was everything I was going to say. I hope you enjoyed, and thanks for your attention. And then you can ask questions. And now you will hear about dynamic sheet pile modeling from Nikolai, who works for Geovita.
Good afternoon. Hope everybody sees the screen. My name is Nikolai Hansen, and I've been working as a geotechnical engineer in Geovita for the past 17 years. I've always been interested in 3D modeling and in developing smart design solutions and workflows, apart from geotechnics, of course. So, as the title says, I'll be showcasing some modeling of sheet pile walls with the use of parametric design. I probably won't go into too many details since I have limited time in this webinar, so consider this to be more like a demo showing the principles like maths, but a bit more detailed on how we use this in our daily work, and to show you what the possibilities are regarding geotechnical modeling, and hopefully getting all you guys inspired and maybe a bit impressed. That said, we will go through how to design 2 dynamic sheet pile walls from scratch to a complete BIM model in around 10 minutes. So I had to turn up the speed a little bit, but hopefully you still get a glimpse of what I'm doing. And obviously I'm not alone on this, so I had a lot of help from my colleague Paul Garborg, as well as the whole team at NGI. So I assume that most of the audience are familiar with sheet pile walls, or at least have seen some of them in some point in their profession. So I'll therefore not go into details about that, but I figure that short intro could be good and useful before we begin to actual modeling it. So in Norway, it's quite common practice to drive sheet pile walls all the way to the bedrock. And in some cases where we have big depths to the bedrock surface, we'll design it as a cantilever wall. And in some cases, we do a mix of the above. So mostly the sheet pile walls are designed as anchored walls with anchors or cables, if you want to, driven into the soil or bedrock as seen on the picture at the bottom right. And in other cases, we're using a single, double, or even triple strutting system between two sheet pile walls, or it could be a single level strutting system which supports against an existing or a new construction, as shown in the illustration above, and like you can see in the picture at the bottom left. So, but again, this is entirely dependent on the construction being built, and often we have to alter the design because of existing infrastructure in the ground, that being water pipes, power cables, tunnels, etc. As I try to illustrate all in the bottom left model screenshot. So I think that's enough about this. So the point here really is that there are a lot of different parameters to take into account when designing sheet pile walls, and it almost differs from project to project. So let's go into action. As you probably noticed from the puzzle pieces on the first slide, we're using the combo Grasshopper, Rhino, and Tekla in our workflow at Geovita. So like Matt's explained, we got our Rhino at the left and Grasshopper at the right, and the only thing we've done beforehand here is that existing terrain, a bedrock surface and a line from a new construction are imported into Rhino from DWG files. So as you see in the top menu as well, we got, we made our own scripts. So you could call it scripts or some small program snippets like the one Matt showed you. So instead of using those predefined scripts, we made our own. For example, we have one script doing transformations, one for sheet pile wall, one for anchors, and one for struts, and some that process the lines that you want to work with. So, and all in all, we got our own little program package in a Grasshopper, as you see on the top of the Grasshopper image. So, and then from this package, we just drag and drop the script we want to use onto the canvas and can use these the same way as Matt showed us earlier when doing the piles. So the first one you see here are doing some transformations. This is due to us working in big infrastructure projects, and we used to and prefer to work in real coordinate systems. But then other disciplines such as architects and structural engineers works in predefined local coordinate systems. And that's why this little script automatically just do the transformation between these if needed. So, and also Tekla works in a local system, so this transformation script will handle the transformation between Rhino and Tekla. And the next script you see at the screen now are something we use here. It's one of the offset scripts. And with that one, you can let us control the distance from our defined constructions line to our sheet pile wall. And then we have the sheet pile wall script, which you see all the way to the right. So here we then connect this script to the offset line script to our sheet pile script, as well as connecting the common basis geometry, and that's all it takes to generate a sheet pile wall like you see here in Tekla. So as you see here down on the left on the screen, it looks a bit odd in world coordinates because of the distance from Origo, but this is more for visual control in Rhino, and the final product will of course be correct, which we'll see later on. So that's why we have those two different views as well. We got the world view and the original view. So let's do another sheet pile wall using a similar offset script, but this time connected to the first one. And as you see now, it's really just a copy-paste operation. So you can kind of use, and we set the distance here to 7.5 meters from the construction line, and connect that one to the other offset component. So it's all fully dynamic and attached to each other. The new wall now came on the wrong side, you can see here. So we just have to modify that in our script. So for it to switch side. And then we can of course change the sheet pile profiles to another dimension, which I'll show you here. So it's linked up to Tekla. And if you want to, you can even add another profile type if needed, that being set, U, or even circular hollow profiles. We can also adjust the length of the walls. So for the south wall, I want this to have a maximum length of 10 meters. And if it doesn't intersect with the bedrock, it would stop at 10 meters length. So just have a look at that. See, that goes to the bedrock here and 10 meters. And the same in Tekla. Let's have a look. The north wall is going all the way to bedrock, and here we have 10 meters sections, lengths of the south wall. So let's model some struts as well. So for this, we need the lines coming out from the sheet pile script and connect them with another offset script where we can specify if the struts should be on a specific contour. Just have to take out the lines here from both walls, of course. We need the struts to go from the north wall to the south wall. So if you connect this, and here you see those little scripts for adjusting the lines. So like I said, it could be a specific contour, it could be a given depth from terrain, and as well as the profile you want to start with and you want to end with. So it's very adjustable. And doing that, we see we got new lines. And we need, of course, two of those, and we connect those to our strut scripts like that. And of course, we need it to have the basic information as well as the terrain and the rock and the transformation. So like you see now, we got nice struts in the model. We got some issue over here, of course, because we didn't define that the struts should only be going according to the south wall. So a quick adjust, and then that's all good. So anchors are done similarly. Our offset line script defining 2 rows. I have this one here, and it's quite a little bit different. It's different depths with input from the sheet pile script, and but then giving an output to our new anchor script. So this one was going in the fix it up, and then as well we need our profile ending. It's okay because it's going all the way to the end. And then we just need our bedrock because we need those anchors to go into bedrock. And you see here we got our anchors, but this was going on the wrong direction, so I'll just adjust that one, and voila. And you see here in Tekla we got our model as well. So but you see a quick check, and in the live link with Tekla and we see something looks a bit funny, you have short segments down to the left, and so we have to change that by just defining a new minimum segment inside Grasshopper. And that's quite an easy fix. Here we got a segment of 12, and then we go back to Tekla and we see it looking much better. So, and now we just did some copy paste of the strut and anchor scripts just to get this full construction pit with a double level strut and anchor systems. So on the level 2 anchor row, you see we want it a bit shorter, so we could easily adjust that as well. Okay. So then it's actually finished. I would like to send this to the structural engineer, but for some comments and so on. And now I already got a message from the structural engineer, as he says he wants to change something in the model. So they need additional distance from the construction to fit the formwork. So we need to give them 1 meter extra space for that. And of course, that's an easy adjustable to do in Grasshopper, as you can see. So, and as you can see, when we move the northern wall, we also define to move the southern wall, and automatically all struts and anchors follows. And then we got another call from the contractor. He would very much like to substitute the HEPS struts with the circular hollow section struts. So, and we are saying, of course, no problem. We just go into Grasshopper and adjust that one. And but just to let him know, we'll probably need double whale beams as well. And like you saw here, it's just a quick two-click option, and we got those double beams as well. So I think maybe a bit fast, but that's the whole principle of how we do the modeling in Grasshopper. So just short going through the method and how to link information to the objects as well. So it's a project-specific attributes like project phase, revisions, and level of details. We are all defining those in Grasshopper as an own script as well. And then we connect this to the desired component scripts, which automatically assign the information in Tekla. And then in Tekla, we'll see it shown like this. And you'll also see an example here of choosing the right one here, and we'll see the capacity of the anchors and so on. And we go to the project specific attributes. You see it's all there directly from Grasshopper. So it's inside Tekla. So that's very nice. So that's kind of how we get the information linked to the models. So our model are finished. I'd like to talk a little bit about collaboration. Like Mats also mentioned earlier, our common workflow would be to export this as an IFC from Tekla and then open it in any IFC viewer which you prefer. So, and as you can see here in one of those, it runs quite smoothly when navigating around in a somehow pretty detailed model as this is. And we'll find the attributes in here as well. And you could even see here, we got our those project specific attributes, as well as you got the base quantities. And I wanted to say you can even do a quick quantity check inside your viewer if you want. For example, if you want to know how many struts there are in the model. And the whole point here is that this is in a viewer and this could be done by anybody. But of course, doing a complete quantity takeoff on a complete model might be better in a more suitable quantity calculation program. And here at the end, you see how detailed it actually is. We got the whole sheet pile. Yes. And of course, for some true collaboration, we could use Trimble Connect in this example here. It's the same IFC. We did import it into Trimble Connect, and we did import the same bedrock surface and existing terrain as we did in Rhino, the DWG files. And of course, you could import existing and new constructions as well as water and wastewater distribution system, among others. But in this case, we just hang this model for in this webinar and the terrain and the bedrock. So another cool thing when we're into collaboration is this to-do action lists. So here I got a to-do from someone who I got this on mail, and you could open this up and you get a whole list of to-do lists of your action points, and you can then directly from your web browser, you can see somebody are asking if we could increase the distance to 4.5 meters. So I guess it's probably the contractor. But just to have a look, we could load this up straight into a web browser. And as you can see here, it's, even though it's in a web browser, it runs smoothly and nicely. And yes, it was a question about having a bit more distance between the struts. Let's see. And like you said, like you could see, the model looks very nice. It's almost realistic and truly reliable. So, and reliability leads us to the uncertainty part. And because even though it looks like it, it's not really reality. So this is a natural lead into our next topic on the agenda, which are how to communicate some of the uncertainties in geotechnical modeling. Just have a sip of water. And I'm not going into details about how to model bedrock surfaces, since this could be done in many ways, from simple triangulation to cracking interpolation, and all with advanced statistic analysis. But often, at least in our daily work, it's a triangulated surface made from boreholes far from each other, and it doesn't really catch up the tendencies, even in a creaking model. So it's like more shown. It's a model shown by the red line in the illustration you see here. And like we saw earlier, when we made our model, we typically design our sheet pile walls all the way to the bedrock. So the thing is that the triangulated bedrock surface in particular makes a questionable uncertainty of the geotechnical constructions. So for example, when doing price estimates of the construction pit in early stages, or even when the road planner are designing the alignment for a new highway or a tunnel. So you can say other consulting engineers, such as the road planner or the structural engineer, are very often depending on knowing where the bedrock are located. And so to say, my experience is that around 9 out of 10 times someone needs this model at day one in the project phase. So the bedrock model are quite important to get started with early in a project. And the thing is, a very early model often consists of very sparse data. So that's quite to sum it up. That's why we think it's essential to communicate the uncertainties in the model, so all parties can take this into account when doing their planning and or design. So you could say it may look perfect, but it ain't, and we don't want this to be our little geological secret. So how are we doing this? At this moment, we use two types of simple uncertainty analysis. One of that are the one you see to the left, analyzing the length of each side of the triangle in a triangulate model, and the other one on the right picture, so that are analyzing the distance to existing boreholes. So even though I already spoiled the result now, I'll still go through and show you how this is done. And for this, we're also using Rhino and Grasshopper to do the analysis part and to tweak the input parameters. So unfortunately, I got limited time here as well, so I will only show you one of the previously mentioned methods. So this is my triangulated bedrock model, which is already imported into Grasshopper. And moreover, I loaded the uncertainty script, and as you can see, we got a couple of choices here. So we just, before we do that, we just set the mesh here. And like the bedrock, I could either import an existing bedrock, or I could make a new one into Grasshopper as well. So the parameters here are for the length of the triangle side. You have some parameters you can adjust. We got a sort of standard at Geovita where we say from 0 to 10 meters, it's quite certain bedrock, and from 10 to 40 it's uncertain, and 40 to 100 it's very uncertain, and over that it's complete unreliable bedrock. Yeah, but of course this is something you have to set on a geological interpretation and knowledge about the project area you are working within. So if you can see the preview here, we got those nice colors, and you could adjust that as well. So it's quite, I think it's too much yellow here. It seems quite certain, so I just want to adjust that one to be a bit more red. So just defined 30 meters here instead, and do a new calculation. Here you see at the left we got more red in our model, so it seems more uncertain. Oh, you can see, and of course it's important to change these as well if someone else are going into the model and should work with it further on. So what about the communication, which was the whole point of this small session? When we're satisfied about this one with the model, it's really just a couple of clicks to export this into something useful and easy to convey to the project team or even the shareholders. So, and since this are linked up, we'll just do a quick export from Rhino here. So how to present it nicely? Yeah. So we got our exported model, and in this example, I took it into a GIS software, and in my case, this was QGIS. So just to have something to present it nicely to the rest of the team. And there's some big advantages here, that it's, for example, open source. It has low system requirements, so it's an easy viewer on a simple laptop, for example. It doesn't really need much, and you can literally add any maps you like, such as Google or Bing Maps or Apple Maps, or even find historical maps, as well as you could connect VMS services if that's the case. So another thing, like you see here, is another nice thing. You could combine it with anything that's already in your internal or project database, that you could import your constructions, alignment, and so on. Or you could easily take your ground investigations directly into QGIS, as I've done here. And this is directly linked up to a PostgreSQL database. So this is I think it's a fantastic model, or yeah, make it's presented nicely. So you could even use this as just a starting point from doing where you want to do additional ground investigations, just to get a more complete model of your bedrock. So to sum it all up, I think this is a very nice and easy way to make nice presentations and communicate the uncertainty. Okay, so again, instead of a GIS software, like I showed you here, this could just as well have been presented in other collaboration software, such as Trimble Connect, Solibri, Quadri, Navisworks, etc. Just to how to communicate the uncertainties to other consultants. And it being a model available and used for making, for example, cross sections. You know, when we imported this color model into Trimble Connect, as you see here in the video, when we're using the clipping plane in Trimble Connect, then we keep all the colors and we see the uncertainties instantly. As well as you see the anchors, you could just do a uncertainty on the anchors, of the length of the anchors. So that could be some point of view, or even the road planner making cross sections, planning the road to the tunnel. It's very, very useful to have this uncertainty model. So, and by all means, you could easily use this in virtual reality or augmented reality if desired. But before we round off, I just have to show you something I find really cool myself. You see, I couldn't quite let our nice sheet pile model that we worked on now for the last 20 minutes, I couldn't let that stay in Rhino all pink and blue. So what I did, I want to make it prettier. I want to present it nicely together with my terrain and bedrock model. So I just here in Rhino cut out the part of the terrain where our construction pit are, and then we are actually ready for some magic, I think. So with only 2 clicks, we'll send it from Rhino to Twinmotion, Epic Games, and we see here it's a direct link as well. So we got those direct link and synchronization that we're kind of found out when we're doing the whole Grasshopper Tekla bit as well. And here see, after just recognizing something, we got our model into Twinmotion. And of course, if we did have some materials in Rhino, it would automatically recognize those. But here I just took it in as it was. And here you can define really your materials inside Rhino. So just to put some grass on the terrain and some asphalt on the road. And as you see, it's just a part of a terrain. So if you want to, you could just put some more landscapes outside our project area just to make it look a bit nicer. And of course, you could make that the same. You could sculpt the terrain, and you could do it here. I think I just turn it around a little bit, and then we just raise it up, raise it a bit down there, like that. And we turn around again just to see what happens, and then we got some terrain inside our construction pit. So we don't only see the bedrock. It's good to have some soil in there. And you could say as well, we give the bedrock some material, and so we just need to to give some material on the sheet pile wall. And since this is, we have the opportunity to make a shine with gold material. So now we have our golden sheet pile wall inside Twinmotion. And just do some more, just put up a little bit more, sculpt the terrain here a little bit. Well, that looks quite neat. So the point is, you don't need to do so much. You can take it all the way to do a nice presentation, and you could use this in different scenarios, like from a website or something. So, or you could play around a couple of hours, and you could make some nice pictures as well. So, like this one I did, and looks beautiful. I think that's pretty cool, and you could do a video as well. So, of course you could. So I did that. If it's running, see, maybe it paused here. So sorry. Yeah. Okay. So while that's running in the background, I like to round off my part of the webinar. So thank you very much for listening, and I hope you feel a bit inspired and learned something. And yeah, this is something we truly believe in, and that will keep developing in years to come. So yeah, again, thank you for your time.
Yes, then I'm on again. That was all for this time. If you want to contact any of us, then you can see the email addresses on this last slide. And as I said in the beginning, answers to the questions will be posted on the landing page, so there you can find them. As I think that some of them are answered already, but everything will be answered on the landing page. This was the first in a series of webinars, and the next one will be held on the 27th of August at the same time as today. So be sure to set aside the placeholder for this already now. The agenda is not decided yet, but information about this will be sent out sometimes before the webinar. Thank you all for joining us today. I hope you found this interesting and that you learned something. And then I wish you all a nice evening, morning or night, all depending on where in the world you are. Thank you and goodbye.